So we have looked at forces in the horizontal. We've looked at forces in the vertical. And now we've also looked at, in the previous lesson, two-dimensional forces. We looked at forces that are applied on the angle. Okay? And we didn't panic when we did that because we already have the knowledge from 2D vectors, and we know that we just need to create the horizontal and the vertical components and redraw a new triangle and solve from there. So we're going to look at inclined forces. So vertical and horizontal forces usually act on the same object, but we always keep them separate. And so we have a F net X and we have an F net Y. If a father pulls his children in a wagon along a flat road heading east, the kids in the wagon have a mass of 65 kilograms. If the father pulls the wagon with a force of 82.3 newtons, 53.9 degrees relative to the road, and there's a force of friction of 26.5 newtons, what is the acceleration of the wagon with the kids in it? What's the first thing that we need to do? Draw a picture. So here's our road with our wagon on it. Okay? And the father is pulling the wagon. Now, how many people have pulled a wagon in their lifetime? Okay, the handle is always here, right? This line, this vertical line is straight up and down. We can translate this line down here to pull from here. It's the same thing, because what happens is when we see this line here, the purple line, we know we need to make a horizontal and a vertical, and a lot of people tend to shut down because it's up in the air. So all we do is we just move that handle down to the bottom of the wagon or the bottom of the object, and now we know that we're just looking at this particular triangle here. Okay, that's all we're doing. We're just shifting it down the line just to make our brain see it a lot better. So the kids in the wagon and the wagon itself have a mass of 65 kilograms. Okay. The father is pulling the wagon handle. So our force applied is actually, if I write in red, can you see? Our force applied is actually this way. That's the way it's pulling. Okay, that's what's actually happening. Force of friction is going to go which way? Remember, the direction of motion is heading east. Which way is the force of friction going to go in this diagram? It's going to go to the west. Now, is this wagon levitating or going through the road? No. So that means that these two forces, force gravity and force normal, are equal to each other. Right? That's where we say, we go back to this concept, force net y is equal to force normal plus the negative force of gravity. But because it's neither levitating nor going through the ground, those balances are equal, or those forces are balanced. And when a force is balanced, this is zero. So all we did in this step here is we're like, they have to be equal to each other because one isn't overpowering the other. It says here that this angle is relative to the road. So that's this angle here, 53.9 degrees. and the force on the angle or on the hypotenuse is 82.3 newtons, and that the force of friction is 26.5 newtons. So this is all the information that we're putting into the diagram right now. What is the question asking us to solve for? Acceleration. And how do we solve for acceleration? What's the base formula? Okay, that's how we solve this question. It's looking for this. So we have mass. Yep, 65 kilograms. We're looking for acceleration. Do we have force net? Nope. So this force net here, which force is friction in? The horizontal or the vertical? Pardon me? Horizontal. It's going to be equal to the force applied in the horizontal plus the negative force of friction, right? That's the opposing force. Do we have force applied X? Yes or no? Do we have a force applied X? No, we need to solve for it. How are we going to solve for force applied X? Well, we're going to look at the X direction here, and we're going to say, oh, well, this is my Y, and this is my X. So force applied X is here, and force applied Y is there. How do I solve for force applied X? Given a angular force and the angle. Perfect. And what do I get for force applied next? Force applied X. How much? .090, like that, Avery? Oh, 490 newtons. Now I've solved for force of applied. I had this information. So force net X is equal to 48.490. Oh, we need to go back and do one quick check. Which direction is force applied X going? East. Is that a positive or a negative? Positive. So this value is positive. Plus negative 26.5. We get what for a value? Like that, Avery? Okay. Okay, now that I have force net X, I can go back up here and I can now solve for acceleration. Good catch. Okay, are we more confident in the 22.34 newtons? Okay. What would my, oh, I know what you did, Avery. You went right to the very final answer. the notes eliminate a step. The notes eliminate this particular step right here, and they go straight to this formula here, just putting this line right here. That's all. I broke it down into 3 individual steps. The notes do it in 2. Yeah, so what happens is in the notes, it takes this particular line right here and puts it in this spot here and writes it out as 48.490 minus 26.5 divided by 65. And then that gives you, I just broke it down a little bit more. If you're comfortable with eliminating steps, that's huge. That shows brain growth. And then this answer here is 0.338 meters per second squared. Is acceleration a vector or scalar? So what's my direction? I heard someone say it. East. Okay. Does that make sense? I'm sorry that it's a little bit different than the notes, but I like showing still step by step by step. Because lots of people, when I skip, still come back for how did you get to this point? All right, let's look at the next example. It says a 12.7 kilogram box is pulled east along a horizontal surface with a force of 60 newtons acting at an angle of 42 degrees. If the coefficient of friction, focus. If the coefficient of friction is 0.230, what is the acceleration of the box? So we're going to Bob Ross this diagram. A box is being pulled east, so our direction of motion is this way, along a horizontal surface with a force of 60 degrees acting at an angle of 42 degrees. So this is 60.0 newtons, and this is force applied. If the coefficient of friction is 0.230, what is the acceleration of the box? Okay, that's how we decode this question, with a picture and all of the knowns that we have. What is the question asking us to solve? Say it out loud, Kyle. Acceleration. How do we solve for acceleration? F net over mass. Now, which is the direction of motion? East. Is that horizontal or vertical? So we're going to want F net x. Okay? So it says, and then here we have force normal. Here we have force gravity. What do we have happening this way? Anyone? Force of friction. All right. So acceleration, we have mass, we don't have force net. How are we going to solve force net? Force applied in the horizontal plus the negative force of friction. Okay. So do we have FAX? Nope. How are we going to solve for that? Because we're going to make a new kind of semi-triangle in here. We're going to have force applied X and force applied Y. Okay, force of friction. We don't have that. How do we solve for force of friction with the information provided in the question? There's a key piece of information given in the question that help us think about what formula we should look at. Coefficient of friction. So do you know that formula, Paulina? Force normal. Okay. We have coefficient of friction. Do we have force normal? What we didn't write down here is this box levitating or going through the ground? No. So force normal must then be equal to force of gravity. Always got to think about that vertical dynamic piece, right? Is it levitating? No. Is it going through the ground? No. Then that has to be a balanced force. So I don't have force normal. How do I solve for force normal? It's equal to the force of gravity. How do I solve for the force of gravity? Mass times gravity, acceleration due to gravity. Okay, let's start doing baby steps back up the ladder now, because now I have this information and I have this information. I have 12.7 multiplied by what's G? 9.81. And so force normal is going to be equal to what? It's going to be different than your notes because I'm doing it baby step by baby step. Yeah. 12.7 times 9.81. Should be just over 120 something. Sorry, I didn't hear you. 124. Okay. Sorry, Avery. 5.8. I'll put a couple dots. Okay, so now we have force normal. We can now solve this one. So I'm just going to go over here. Force of friction is equal to U Fn. I got 0.230 times 124.58. What do I get for a value there? How much? Okay. Now that I have this piece, I just need the math for this piece here. Cos of 42 times 60 newtons. This value here. Yeah, how much? All right, that's force applied X. All right, here's something that we need to consider. Where am I going to put this? I'm just going to put this on another sheet. So this is being pulled like this. And we said this was force applied. This was 60.0 newtons. This is, what did I say? 42 degrees. We said that force normal worked this way. Force gravity worked this way. Force of friction worked this way. Let's look at some characteristics. Okay, do we agree to this diagram and everything that's how it's labeled? Yes? No? Yes? Okay. What are the pieces that are in the horizontal? Okay. What's in the horizontal? Or in the vertical, I mean, sorry. Okay. When we look at force net X, what would we write here? How would we set up this particular formula? Okay. If I was looking here, what would I say for force net Y? What about this guy here? It's an we just identified it as a vertical component. Which direction is it moving? Up or down? Whoops. Which direction is it moving? Up. We need to account for force applied in the vertical direction. Okay, stay with me. Is this box levitating or going through the ground? No. So this is a balanced force, which means that force normal is equal to force gravity minus force applied Y. Do we see that piece? Thumbs up, thumbs sideways, or thumbs down? I'm okay with sideways. I'm even okay with down. When we are looking at forces, we have to look at the entire system. And in the previous question here, it asked us to find the acceleration of the wagons with the kids on it. And we were looking at force of friction and force applied X. We didn't need, when we did this formula, we had force of friction given to us. We didn't need any other piece of the system. In the horizontal, we were satisfied. When we go to this question here, and we look here, we say that the force of friction, we don't have that piece of information, so we need to relate it to the vertical position. And in my haste to solve the problem, which should indicate to you that this is a common error, I ignored this very critical piece right here. This is a part of the system, the vertical system. We're now including that vertical piece. We have to. We have no way of solving force of friction. It's not given to us. We need to now look at force normal to help us solve for it. This equation right here draws in the vertical components. So when we go to this step here, we're only partly right here. We need this piece here. Whoops. Force normal is equal to force of gravity, which we solved right here, minus force applied y. Because we need that vertical piece. So this is 124.58 minus, what would force applied y be? How would we solve this piece here with this diagram? Sine of 42 times 60 is equal to what? How much? All right, so 40.148 newtons. Now we can say force net is equal to, or not force net, sorry, force normal is equal to what do you get, princess? 439. Okay, I used the rounded number, so I'm just going to put that, but you write down what you got, okay? So now we can go back up, make the correction here, 84.432, and we can say that it is equal to oh yeah, I got that. Anybody get this number or very close to it? For force of friction? Yeah, perfect. Okay, I've satisfied this piece. I've satisfied this piece. Now we can go back and we can do this piece. So force net X is equal to what do you guys get? How much? Okay, I'm just going to write down my number. You write down your number, okay? Because again, I didn't use the full numbers all the way through. Now that I have force net x, I can actually now finally solve for force acceleration. Oops. What did I do? Put the wrong numbers in. This is not my day to math. 12.7 kilograms is our mass, not 60. So why, this is not going to work all the way through. We put the wrong numbers in. We put the force in instead of the, oh, well, that was right. That was right. We did that right. Never mind. Today must be my Monday. What do we get for a value when we put the actual right numbers in? One point what? Perfect. Imagine that. When you put the right numbers in, you get the right answer. Acceleration is a vector, so which direction is this going? East. Let's put a box around it and call this question done. Kyle. Yep. So with the aside of I messed up a few numbers, do we understand this concept of looking at all of the pieces and understanding where all of the different forces go? Thumbs up, thumbs sideways, thumbs down. Okay. Avery, can you put a word to it?